Do something hands-on. So what we'll do is I'm going to use the R package. So R is actually a very nice language and a framework and a system actually to do a lot of data analytics. So it's very, very popular. It's used extensively, for it has a very powerful set of statistical tools, and many packages are available for R. And I like Python equally well. Python with the numerical Python library, a module, and many other network packages for Python. So for some reason on my laptop I have a very old version of Python, so I cannot, I would have used that one, but since I don't have it, I'm going to use R. So one can play with these systems because they let you interactively manipulate things. So this is something that I would encourage anyone who wants to do data mining, machine learning. You can sort of do the MATLAB way, right? If you have MATLAB, but R is free. Python is obviously a good scripting language. So I always interchange between these two whenever I teach a course or do my own coding or analysis. I like R, I like Python, and I sort of keep on switching back and forth between them. So if you don't know R, I encourage you to learn R. But it's very similar in for any other scripting language for that matter. So in this R, what I've done is I've installed this library called iGraph. So it's a graph library. So I'm just going to load it up. So you just say, just like you say import, You have Python?
But we have
You have it.
I have both.
It's all right. The point is just to see, if you have installed Network X in Python, you can do the same thing. Hopefully. So yeah, let's start with a few. So whatever I'm doing here, we can do either one of them. So maybe I should have just kept one. Yeah, that's fine. So the first thing is that we have to create a graph. Right? So in this one, what I'll do is I'll start with my with a ring graph. So let's see. Oh, okay. You can't see it back there? That's a good question. Can I increase the font? Yeah, it's a bit too small, huh?
Can you maximize the font?
Let's see.
So it's an edit GUI preferences. No, it's an edit and GUI preferences.
Oh yeah, okay, good. Yeah, thank you. Can you see it? Now I can. Okay. Hopefully that, if it's too big, yeah, I think that's fine. Okay, so I loaded that up, and now I want to make a graph. Let's see if this works. works here. Even I know that normally statisticians like to do it that way. Let's see. Circular. Actually, there's my manual and my iGraph version is a little bit different. So let me say this one. Oh, it is?
It's G and arrow, I think. G second equal to G equal to make underscore ring and fraction. Yeah, give me the moment.
Sir, STR make it.
Less than and dash.
I know, but that should not be.
Sir, it's STR make it.
Sorry?
STR.
STR?
STR make it. STR bracket start.
Okay.
STR.
And ring?
Make ring. That above.
Like that.
No, it's working on my
Sir, only
It's working on the machine also. Because I have a
Yeah. Actually, I did something with that. Let's see, what is the format for this thing? So we can look up what the format should be. Okay, so this says, oh, now I got it. Okay, graph.ring. I'm sorry, this is the old version. So, okay, so now I see. So, G is equal to graph.ring. And now I can put 10. So now I can do, so the R, it has inbuilt functions, so I can say plot G, so it will plot the ring-like structure, right? So we have this. So let me add a few, random connections, then we can study the properties of this network. So let's say I say G equal to add.edge G. Okay, so in R, a vector is given by the C function. The C function will return a tuple. So I'm going to say add an edge between 1 and 5. Okay. So that should give me a new graph with the extra edge in it, hopefully. Okay. So I'm going to plot it to see whether it works. It's actually probably back. Yeah, so see what happened to the ring is, of course, I added that link from 1 to 5, right? And let me add one more between, let's say, I don't know, 3 and 8. So I'll say between 3 and 8. And now I'll say plot again. Okay, so this is the graph I'm going to basically, we can look at some of the properties, we've gone through last time. So this is a good hands-on way of checking, some of the things that we covered in the last class. Okay, so the first thing we can do is, maybe we can do page rank, right? So do you want to do page rank now? Actually, that's a little bit, okay, we'll get to page rank as the last thing. Let's do some basic degree distribution, right? So the iGraph has lots of built-in things. So, I could put them up, but since we have them here, so let's first find out about the diameter. So I want to know what is the diameter of this network. So you can I think just do diameter. So you can say diameter of G, and it says the diameter is 3, right? So this network has a diameter of 3. but it did not tell me what the path was. So I need to know what was the path corresponding to that. So that is the get diameter set. So I can say get diameter, or is it get dot diameter? I'm not sure which one. Get diameter, and then I give the graph again. And this will actually now return to me the path. And you can see there are 4 vertices on that path. That means the number of hops is 3. So 1 to 2 to 3 to 8. So you can see it's basically starting from this 1, you go to 2 to 3 to 8. So that's the longest path that we have in this network. There may be more than one. It will just return one of the paths. So it's not just this is the only path that satisfies the diameter constraint. So we can do that. Let's see if the betweenness we can do. So I want to know, is 1 a between node or not? So let's see if I can compute actually no, before that we can do we can compute the distances. So a lot of these metrics, right, they're built around the distance matrix. So we need to know, by the way, is everyone on the same page? I mean, for those of you who are, everyone using Python or R, or how many are using R? Okay, good. So then we have a good camp. So everything depends on the distance matrix, right? So many of these computations are based on distances. So let's compute the shortest path. And so there is a function called, I think it's called distances. Let me check. So I've kept this, this manual as a guide for me to quickly check. So I believe it is distance table, maybe. Okay. Let's try the distance table. So I can say distance table. Distance. I don't know if this will probably not work because I can't find this function.
So this distance is function which will return a table matrix.
Okay, so it's not okay, good.
Distance is
Or G dot distance? No. Yeah, actually that's why this somehow my version is a little bit older, I think. Shortest path. Yesterday. What version is getting in trouble? Yeah, mine is just.
So you want to use this? This is the latest version. So
Okay, that might make it easier.
नेट कनेक्टेड है कहाँ है
So let's see, change the view here. Okay, so, alright, so I guess the point was that, so yeah, if you look at this command, which is working, for me I think I have an old version somehow in mismatch. So this one gets you the complete distance matrix, right? So you have essentially, when you call the distances function, it gives you all the distances from every vertex to every other vertex. So it's n by n matrix. So from this, actually, we can, one second. So this one, okay, let me plot the graph and see. Okay, there's one edge missing. So let's add that edge because here in this network, which is without that second edge, the maximum distance was 5. Okay, so the diameter of so you can do the max, right? So you can compute the max of, so I can just say max of x, and that would have given me the distance, the diameter, of course. Well, it's right. Oh, sorry, max of x. If that works. Yeah. So that would have given me the diameter. But this is for the for this graph where the 3 to 8 is missing. So let me add that so that we're all on the same. I think everyone added that. So G is equal to add edges G C 3. And now I can do the same thing again. Compute the distances, and now I can show the distance matrix, and then I can do the max. And this was the same value we got from the diameter function, right? So you can do it this way. Let's see if we can do. Let's see if we can find the betweenness. So let's say what is the function for that one? Betweenness, that's it. So this will compute. So I mean, of course, this iGraph library has many other things pre-computed. But normally, what I recommend is that it would be good to implement some of these things on your own, right? Because it's good to sort of just play around and get these numbers, but the real sort of value would be to actually implement the code that will compute the betweenness. So you have to look at all the shortest paths, and in this case, you actually have to enumerate them. You have to find actually each and every shortest path, and then see which of them contain V, and then find the value from that. But let's see this one. So this returns the value for the betweenness for all the vertices. So we can look at this and say, okay, vertex 1 has betweenness 8. So in fact, this one, 9 is the highest. So who is 9? So there was 10, right? So this should have been, should be vertex number 8. So let's look at vertex number 8. Plot 8. Okay, so this is this 8 one is the most between numbers. So what that says is that if you look at the shortest paths in this graph, a lot of them are going through 8. Actually, one second. So this I have to see what it is an edge between. Yeah, there is a node between it, right? So in R, you can always put this question mark in the front to, if you want to know the the description of that function. So it opens up a page with the computing the. Let's blow this up. So there's a good way of checking what the parameters are, how they compute the thing. So if I look at this betweenness. So this says, what are the input parameters, right? So you can do the graph and the vertex. Excuse me. You can give whether the graph. So this is doing by default directed is true. So I wonder if I put if I change it, if it makes any difference. Let me try it just to see if the direction. So you see the default parameter here is directed being true, but our graph is not directed. So does it matter? Let's see. Maybe it automatically figures out that it's not a directed graph and it does the right thing. But I just want to make sure. So if I do this again and I say directed equal to false, and let's do what happens. So yeah, nothing changes. So I think it's of course smart enough to figure out that it's nothing. If the input graph is directed, it will use that as the. Okay. Where was my? Okay, so the other thing I want to see here is you can also do edge betweenness, right? So maybe you want to know. So this previous one told us which was the most between. But what about the most between edge? So the edge, the betweenness idea can be applied to edges. And edges would be, in a transportation network, in a logistic network, this makes a lot of sense. Because the edges are what matters. And the nodes are just the intersection points and things. So we would probably want to know what are the edge betweenness. So let's see what the edge betweenness tells us. Alright, so now the issue is that which edge is which edge. So I think we have to print out the list of edges. Okay, so edge list. G dot edges. Edges. Alright, so I think from this we should be, I think it returns it in the same order. So, to the last two, the 3, 8 and the 1, 5. So let's see, 3 to 8. So that actually makes sense, right? You see how I created the graph? And this is intuitively the right thing to do, right? I started out with a ring, and the ring was all connected to the left and right neighbor, and I actually added 1, 5 and 3, 8 as the connectors. So now you see that actually 1, 5 and 3, 8 are the most between, because that's where the shortest paths they go through those. So I think that was a good sort of reverse engineering that these are the critical paths that connect the network. So that would be the thing, that if you want to disrupt this network, right? So if you're thinking like from a malicious point of view, so it would be very easy to disconnect this network. The thing would be you would disconnect 3, 8, 1, 5, right? So these are the sort of the vulnerable points in the network. Sorry, you have a question?
Yeah, after you write the edges and this result.
Oh, okay. So yeah, so this edges, because when I did edge betweenness, right, it returns a bunch of values. And I didn't know which edge it was. So how do I find out which edge? So then I put the edges of the graph. And the edges of the graph, basically, this is the part that we have to look at. So the edges are 1 to 2, 2 to 3, 3 to 4, right? So that's our cycle, right? 1, 2, 3, 4, all the way up to 9 to 10. And then the last two edges are added, 1, 5 and 3. So there are, there's a ring. So this actually says what type of graph it was to begin with. It was a ring graph to begin with. So let's not worry about that. These are the list of edges. And I can look at these, and so these numbers are in the same order. Okay, so the last two numbers are 10 and 10, and they apply to the last two edges. So the 3 to 8 and 1 to 5. So I can correspond the number to the corresponding edge.
This edge between it's not 6.5, it is 6 and 5. These are the edges, it is.
So 6.5 is the betweenness value, and the edge is the edge from 1 to 2. So just to find out which edge corresponds to that. So R basically internally maintains, the iGraph library maintains the order. So every edge has a edge number, and so this will just print them out in that order, but we don't know which it was. So just to see which edge was connecting, we can print it out to see that edge corresponds to this. Okay, so now I'm going to do page rank. I want to know the page rank of this network. So first I need to get the adjacency matrix, right? So let's pick up the adjacency matrix. Hopefully there is a function that will give me the adjacency.
Sir, is there a mathematical relation between betweenness and node betweenness?
There should be, yeah, there should be. Most likely, the endpoints of the between edges will have higher between nodes also, right? Because the flow is going through those edges, so obviously there should be a link between them. So I'm trying to see what is this adjacency matrix. How do I get it? That will give me only for one of them. Let me see. Okay, we can create our own. I mean, this is a little bit tedious. So what I'm going to do is I'm going to use a trick. So this no, but this is the shortest path. That's not going to help me. Oh yeah, okay. So in fact, anything that's a 1 is correct, right? If you have a shortest path of 1, you're adjacent. Otherwise, you're not. So maybe I can use this to help me. So I can say, so I'm going to basically change this. So for I go from 1 through 10.
One colon 10. So 1 colon now.
I have to enclose it also, yes? No? No. Not required? Well, there's more than one way to do this.
don't have to put those parentheses for the loops.
For the
loops.
is it? No, but this is saying for I. What am I doing wrong?
That
I forgot now. So this is what happens when you do a.
Okay, say enter. Say enter. For I is equal to 1 to 10.
This? No. How did you afford to be? This is when you conflict between Python and R all the time. I don't know how to do for it. You should know.
Sir, ये brackets equal to ये in है. For I in one.
Ah, yes. For I and yes.
And it will be in brackets.
In brackets?
In brackets, yeah. I in 1 to 1 whatever. Yeah.
Aha, that's it. Good. You're close. This is better. See, I knew the brackets were there. Yes.
So curly braces.
Anyway, this is a very hard way of doing it, but I'm going to do this. Xij is equal to this. Okay, so now let's do this. So this is the adjacency matrix. Because right, the distance of 1 was the direct neighbor. Anything higher was not your direct neighbor. So this is, hopefully it's correct. I think we can verify 1 to 5 is correct, and 3 to 8. 3 to 8 is there. Yes. Okay, good. Alright, so now we have the adjacency matrix. So what I have to do now is I have to make the degree matrix. Okay. So I'm going to make a degree matrix as follows. So every row should be divided by the degree of that node. So the degree matrix is actually very easy to do. You can just sum up the rows. There is a function in R called row sum. So I can just do row sums of x. And then what I want really is I want a diagonal matrix. Okay, so I'll tell you later, this is called the degree matrix. This will be important in later chapters. So you just put a diagonal matrix, and you say diagonal of the row sums of x. And that will give me a matrix. But let's first look at the row sums of x are the degrees of every vertex. Okay? So vertex 1, 2, 3, 4. So the row sum is simply taking that matrix x and just adding them up. But this is a vector of degrees. So it's a degree vector. But I wanted the degree matrix, so I did the diagonal, so I did this diagonal of the row sums. And this gives me this matrix D, which is a very important matrix, by the way. It puts the degrees on the diagonal. Okay? And so what this allows us to do is it allows us to do, we can multiply two matrices to do lots of interesting operations. But what I want is I want to divide each row by the degree. So first, instead of the degree matrix, I want the inverse of the degree matrix. Okay? So I'm going to call this matrix the ID matrix. Okay? The ID matrix is going to be the inverse. So it will be 1 over the degree. Okay? Because every row has to be divided by the degree. And of course, if it's a 0, I have to keep it a 0. I can't do 1 over 0. So I can't just say, I cannot say just 1 over d, because this would give me, this operation, by the way, so R is actually highly optimized for matrix operations. So if we just do 1 over d, it will actually divide every entry, it will put that entry, it will want to be 1 over that entry. If you do this, unfortunately what happens is that you will get infinity because you're doing 1 over infinity, right? So we don't want that. So instead what you have to do is you have to sort of redo what I did before. You have to say the diagonal of 1 over the row sum, okay? If I do it this way, first I divide the degrees and then I make a diagonal matrix out of that. This will give me the right matrix. So this will give me the matrix I want. I have to expand this a little bit to see. Anyway, the way to read this matrix is, it's because we have these, you can see the first row, the first entry is 1 over 3, 1 over 2, 1 over 3. So this is the diagonal that's going this way, and the diagonal then continues on from here. So it's just the matrix has been split to display it, but it would be a diagonal matrix. Now, once you have this diagonal matrix, this is one of the key operations that we'll look at later. If you want to compute the Markov matrix, the one-step matrix, I can define that to be the M matrix. And the M matrix is actually ID multiplied by the adjacency matrix. So this symbol, percent star percent, is actually matrix multiplication in R. So when you do this, what are we doing actually? Remember, X is, actually let me do one more thing. Let us say that A is equal to X, okay? So A is the adjacency matrix. So remember, A is this matrix of adjacencies. ID is the diagonal matrix of inverted degrees. And now I'm going to define my Markov matrix, which is every row divided by the degree. So M is going to be the inverse of the degree matrix multiplied by the adjacency matrix. Anytime you multiply a matrix on the left, okay, you're doing row operations. Anytime you multiply a matrix on the right, you're doing column operations. This is the key, simple sort of mental picture you can have. So by multiplying by the degree on the left, essentially what you're doing is you're taking each row, and remember this is a diagonal matrix, so each row has only one number. You're dividing by that number essentially on the left hand side. Okay? So every row will be multiplied by the inverse of the degree, which is what we want. So this will give me my Markov matrix. So I can quickly verify this works. So if you look at this matrix, look at the first row. The first row, all the entries should add up to 1. And I can easily verify that, right? So because it has to be a row stochastic matrix, I can say, if I say row sums of M, I get 1 back, right? That means every row has been properly normalized. Okay, so now all we have to do is to run the page rank on this. Remember, this is a symmetric graph, so M and M transpose are the same thing, we don't care. So what I'm going to do is I'm going to initialize my page rank vector. So I'm just going to call it P. And I'm just going to define a vector with 10 numbers. And, I'm just going to, so I can just define a vector this way. 1, 1, 1, 1, 1. 1, 1, 1, 1. There are 10 numbers, right? Okay, 10. So P is my initial vector. And just to make sure, we don't really have to do this. And let's not do it. Okay, so I'm just going to use this vector as my starting point. Normally you can normalize that to have a unit length and all that. We'll do that in the end. So what are we supposed to do? We are supposed to do a matrix vector computation, right? So we are supposed to take this transition matrix M and simply multiply that matrix on the right by the vector P. So that's what I'm going to do. So I'm going to say P is equal to M times P. M times P. Right, so essentially it will compute the matrix vector multiplication and put the new result in P. So let's do that and see what happens. So P, in this case, sorry. So So actually it's easy to verify. Let's do it. Right, so that's the advantage we have now. All I have to do is rerun this whole thing. Actually, first I have to set it up. So let's see what happens. I mean, I think it may have some trouble, but it's kind of like counterintuitive what it will do. Which is, I think, what we think should have happened, right? So you're saying that basically keep on walking, as far as you can get, because it's like the inverse. So basically you end up being equally likely in any part of the network, as if the degree nothing matters, as if the structure is not there. You basically end up in pretty much the whole network. So now you have an answer. That's a good. Yeah, that's a good idea. Or I can just maybe save it, right? Save to fire. So last thing, I'm just going to call it. Okay. It can be loaded up? Okay, I will not kill this yet, so we'll keep it. Okay, so I think that's all I have to show for today.